All right, let's see. It is 1:03. I think I've got a lot of stuff to go through because there's all kinds of interesting and exciting things to say about AI hardware. So we'll go ahead and kick off. Um, this will be, I'll just mention this in the recording. All these recordings are saved and recorded and held onto, so we'll be able to toss this up into a channel in case we cover anything that you want to go back to and listen in again, or take a look at the slides or something like that. These are all recorded and we post them usually like a day or two after the event. So if you want to check out whatever we covered today, please feel free. And if you'd like a copy of the slides, you can just send me a message. Cool. A couple housekeeping things. So once again, welcome. This is part of a year-long series that we're hosting, Mozzie Tech Talks. Every Friday at 1 p.m. we'll be here to talk about some topic related to artificial intelligence. And today it just so happens to be AI hardware, which is something I'm very excited about. And I think we should have a good conversation coming up here. After the talk, every week we get together on the general channel. So that's a great way for us to just discuss the topic. If there's any items that come up that you'd like to ask questions about, or you have more to share, or you have a correction to make on something I said or something one of our other presenters said, we just would love to have that conversation. So feel free to join us in the general channel if you get a chance. For those of you who are here for the first time, maybe joined our Discord before learning about sort of our product and our platform, welcome. We're so excited to have you. I'd really encourage you to sign up for a free account on Mozzie.com. We've got somewhere between 40 and 50 of our machine learning models available there. You can get access to all of our docs, play around with the API, build your own apps, play around with some of the features we offer, like explainability, and just generally, see what we have to offer. I think you'll like it. And lastly, if any of you are interested in contributing to open source, two of the open source projects that we sponsor, Chassis ML and the Open Model Interface, we're looking for contributors. So if you'd like to take part, check out those two channels within our open source section on Discord, or alternatively reach out to Clayton Davis. And we'd love to have you. We actually have a bunch of projects that we're in the middle of, and have some pull requests and other tasks that could absolutely use a new set of hands. So if you're passionate about open source, excited to meet with you and talk with you more about what we could do together. So with that, let's go ahead. Oh, one more thing. Remiss to forget to mention that we've got some upcoming talks planned. Kind of the next month or so is lined up. So next Friday, you'll be joined by, I believe, Brad Monday, talking about automated model deployment pipelines. Then we're going to get a little bit of a demo on how to use Mozzie with Tableau, courtesy of Brett. And then finally, the end of the month, we're going to be showing off a pretty cool demo of our new chassis feature set, and the integration that we built into Mozzie to connect chassis and Mozzie together for automatic model containerization. So that should actually be a pretty cool demonstration as well. So some really neat talks coming up, and hope you guys can join us for those. All right, time for our Tiger King themed talk on AI hardware. If you haven't seen Tiger King, hopefully the talk is still good, but you will miss some references, so my apologies. The first thing we need to talk about before we talk about artificial intelligence, accelerators, and hardware for AI is computers and how they work. The main concept that's allowed us to get to the point we're at today, where thousands and thousands and thousands of people are writing software that run on computers, is by breaking up the ecosystem into a lot of layers. And at the very bottom layer, it starts with physics, which is just electrons moving around. And through a series of hacks and tricks, we've convinced those electrons to do work for us. We've done that in the form of logic gates, and building on lots and lots and lots of logic gates, we're able to create custom hardware. Everything above that, machine language up through the OS, isn't something we're going to talk about today. There's all kinds of cool stuff that's happening at that level. But today we're really going to talk about that hardware layer. And, how is this all possible? And what happened in history that got us to this point? Well, the big answer is abstraction. Each of these layers is an abstraction of the layer underneath it. Ultimately, we're still all just pushing a bunch of electrons back and forth and tricking them into staying in one location for a little bit before they move along someplace else. But we've been able to create enough layers of abstraction where if I want to move my mouse around, I don't have to weld a new connection between 2 points on a chip. We've created the mechanisms where we can separate out what's at the hardware level and below out from the software layer and above. And one of the big reasons for that is a guy named John von Neumann, a guy born in the early 1900s in the, Austro-Hungarian Empire, I believe, who ended up migrating to the US, worked at Princeton, and he developed something that we refer to as the von Neumann Architecture. And that is, generally speaking, the same architecture that's used today for any central processing unit, but it's really refactored into a whole bunch of other types of hardware as well. And the basic idea is that we're able to break down the processing of really small mathematical functions into individual discrete steps. And the main components of this architecture are memory. So this is the ability to store either a piece of data or an instruction. So that might be the number 7 and the instruction add. We're able to store those in memory. We're able to reference those via a register. And then we're able to execute both those instructions add and those pieces of data through what we call the ALU. And that's the arithmetic logic unit. All of that is managed and controlled using a clock. So he's actually a mathematician, and he developed this concept as an abstraction on top of what was happening at the time in the hardware world, which was, at the time was really vacuum tube-based computing. And so this structure, this architecture, has actually lended itself to huge advancements and has gotten us to the point where we are today, where to program a computer, you can create a set of instructions, load those instructions into memory, and your registers, your ALU, and that control unit are actually going to step through every step of the program you wrote and do that job and do it really well. And if you want to change that program, you just have to change what's in the memory. Before that, you'd actually have to reconnect computers with physical lines, and it could take 2 or 3 weeks to reprogram the computers of John von Neumann's era. So this whole paradigm shift of us being able to write software has been a game changer, and is the reason why we can do all the crazy machine learning and artificial intelligence stuff we can do today. And this architecture is still woven heavily into a lot of the hardware that's used. So let's talk a little bit more about that and what that looks like. We're going to start with the maybe least exotic piece of hardware out there today, the central processing unit. And by and large, CPUs have not changed significantly from that von Neumann architecture. But what they have gotten is some tricks up their sleeves. So what you can see here are 8 cores, each of which has that von Neumann architecture inside of each of these boxes. But one of the challenges that the architecture ran into early on is something called the von Neumann. What was the term for it? Essentially, it's a constriction in data transfer, and when computers are doing their job, the register is basically grabbing an instruction from memory, add, and then grabbing some numbers. It has to reach out, get that piece of information, move it to the bus, and then move that to the ALU. And in the 90s, some analysis was done where basically 3 out of every 4 clock cycles, which is basically steps. The clock is kind of like the big conductor of the computer, and it tells everything on the whole system when to move forward, when to take a step. 3 out of every 4 of those steps were wasted, like no processing was happening. So to get around that, they started developing really complicated and sort of tricky tools to help bring more data as close to that logic unit, that ALU, as possible. And they do that through caches. So there's something called the L3 cache, and right here you can see that's all shared across all the cores. And then inside of each core, there's some other caches, an L2 and an L1 cache. And the basic idea there is to try and get as much data as close to that ALU as possible. Because what CPUs do really darn well is they do a linear set of functions super fast. So if you want to process, 1 million numbers in a row, sort a big long list, CPUs are fantastic at it, as long as you can get them the data fast enough. So for a number of functions, and particularly because of their flexibility, CPUs are like the workhorse of computers, and that really has not changed significantly in 80 plus years. Now, if we zoom in one more level, what we can see underneath all of this is the transistor man. And what the transistor man is doing is reading in the physics of these chips. And this transistor concept, is really what brought this revolution to the forefront, where we're able to send a really small voltage and use that as a way to store data. So really small combinations of these little transistors that take in two inputs and either send an output of 1 or an output of 0 based on the values of those inputs. We've created everything we know today about computers. And so these transistor units are core and elementary, and every piece of hardware we talk about today is still built on this exact same piece of tech. They've just rearranged them in slightly different ways using different kinds of abstractions. So the final thing I want to say about CPUs is they are not identical. They're still using similar kinds of concepts, but there's actually more than one architecture and more than one what's called instruction set. The two most common, the really only two you have to think about and worry about, are referred to as ARM and x86. So x86 is what Intel uses. It's been around for a long time. And if you look at performance benchmarks in terms of just how fast this CPU can get its job done, they tend to win out. They are very efficient. Any enterprise-grade server that's really there to do a workhorse type job, high-performance computing machines, they typically are using these x86 processors. They're super powerful. At the same time, they're very power hungry. So enter ARM. ARM is a different architecture. It's a standard, but it's not made by one single company. And it's used by a lot of companies that are designing their own chips. They have adopted this ARM architecture. And what's really nice about ARM is tends to be lower power consumption, and it has awesome performance in terms of speed per dollar. So if you're trying to go for like high speed linear computing, an x86 chip's probably going to do a great job for you. But if you're trying to do something that's both performant, low power, and not too expensive, then ARM chips are the way to go. And that's why you tend to see ARM chips used almost ubiquitously in handheld smartphones. When we're trying to get the price of these things down as low as possible for the average consumer, you want to use the cheapest but still performant chip you can get. Now, why does all this matter for us as we try to figure out how to use hardware to do machine learning? Well, the main reason is these instruction sets. Each of these CPUs has a different set of instructions. Within the ALU, that algorithmic or arithmetic logic unit, they have like a set of jobs that they can do. Those ALUs can do, let's say, 1,000 jobs. And so if you want to add two numbers, there's an instruction that you have to ask the CPU to execute. And that instruction has a number. So let's just make it up and say the number for adding is 12. You have to tell the ALU, hey, I want you to execute function 12. Well, for ARM, that might be to add two numbers together. But for x86, that might be divide. So if you write your program, right, you're creating code and it's getting compiled, and we figured out how to turn all of the characters we've typed into Python into a bunch of binary bits and bytes. We're sending those to the CPU to do a job. Your instructions are different. So the instructions you send to ARM are not going to work on an x86 chip and vice versa. So the important thing to remember here is you're making these decisions and you're trying to decide which of these CPUs might be a good fit for my ML use case. You're going to have to create different programs. You're going to have to compile different programs for each. And that's actually something that we've done and have added into the open source project that we've started, Chassis, to actually help our data science friends and colleagues achieve this more efficiently and more effectively when they're creating machine learning containers, because this can be kind of tricky to handle. So keep that in mind so you don't get hung up there. All right, we're going to shift gears a little bit, not stop talking about ML for a moment and talk about TV screens. So TV screens are made up of lots and lots and lots of pixels. And modern TV screens are rendering millions of pixels up to 60 times a second. What that turns into essentially is being able to transfer tens to dozens of gigabytes of data per second. And in fact, I think the latest version of the HDMI cable is capable of supporting 60 gigabytes per second of data transfer. So when you just think about that and how fast the internet works, It's kind of mind-bending that we can send that much data to a computer screen all at once. Well, this started to become a problem because CPUs were not able to keep up with the task of calculating every single point on each of these screens as resolutions increased, as frame rates increased. So the whole computer world started to develop a new pattern, a new abstraction, where all of the math needed to calculate pixel values was offloaded onto this new device called a graphics processing unit, graphics card or GPU. And these machines would focus on a really limited set of tasks. So instead of being super generic like CPUs, they focused on doing a couple of things. This could be calculating shader values. So when you're rendering a 3D scene, being able to calculate how light reflects off of different objects and the shade that they cast when they do so. This is a really special kind of math, and if you can build a chip that does that math really effectively, you can do it faster. And the big idea here is that when you're trying to render an entire frame, every single one of these pixels on the screen at once, you need something that has a lot of throughput. So you need something that can really generate a lot of outputs very quickly at the same time. And that's something that GPUs do very, very well. Now, what does that look like at the actual architecture level? So we talked about a CPU before. This would be an example here of a CPU with 4 cores. It's got some RAM. It's got this cache that's kind of holding on to the next set of both instructions and data that you want to add or divide or whatever. Then you got this control unit, and that's doing the stuff to actually move the data around your cache into the register and then into the ALU. And then each of these ALUs can do their things. So again, adding 2 numbers, dividing 2 numbers, and then sending the results back into RAM. What a GPU does a little differently, and you can kind of see this here, it actually has a different set of cache and control logic attached to a whole big bus of miniature ALUs. Now each of these is much less powerful, so it cannot do nearly as much work and cannot do that work nearly as fast. But as you can see, there's just a lot of these. So well, here with a CPU, you might have 4 logic units that are able to do 4 things at once, super, super fast. The GPU can do hundreds of things at once. Now each thing is slower, but when you add it all together, it's actually much more performant for certain types of use cases. Now let's shift back to why this is useful for machine learning. With classical machine learning, it doesn't really have that much of an impact, that much of a difference. But with the introduction of deep neural networks, this architecture approach of being able to do multiple kinds of math all at the same time ends up being super helpful. And the reason for that is deep learning is based on matrix math. And if you guys want to recall, sophomore year of high school math class, where we learn how to multiply matrices, essentially what we're doing here is multiplying each of the items in these rows of data against each of these columns of data. And for a really large neural network, the number of rows and the number of columns can be in the millions. So if you can kind of just imagine how much more efficient it would be to be able to calculate W times X 1,000,000 times at the same time versus trying to calculate W times X all sequentially in a row and then adding the results together. And it turns out to be that the logic of that is very sound. Because you're doing really small, not super sophisticated or super complicated math at once, you can get huge advantages in throughput. So what GPUs specialize in is throughput. It's getting just a whole bunch of data pushed through the hardware really fast, whereas CPUs can send data through at very low latency. So if you look at an individual thread, for instance, this GPU is doing 4 threads, and it's doing them all at the same time. And there's a lot of time wasted waiting for data because the same bus is being used to kind of move data back and forth and grab instructions and data from the cache. So each individual thread is taking kind of a while compared to the CPU, where this first thread is done in a third of the time. However, the CPU then has to go and start the next thread because everything's sequential. It only has up to 4 in some cases, maybe 8 cores within your CPU. But the GPU has millions of these things. So when you're doing something where you can do all the math at once, huge efficiency boost. Something else to know about GPUs is that they're not all the same. You can use GPUs sort of in different modes and for different purposes. So one of the ways that typically GPUs are most useful is in training. One of the reasons why they're so useful in training is that you're doing a lot of math when you're training a neural network. It's just so much matrix math because you are doing this forward and this backward propagation where you have to do all those matrix multiplications and additions like a million times in a row. And you just do that over and over and over again until you have a model that's stable and your data scientists say, yes, this looks good. Like I like how this model's performing. Because it's a flexible architecture, despite being a little bit more focused on one job than a CPU, it's really useful for this function. But you can also use GPUs for inference, and that is taking the model that's been trained and done all that math on and running data through it in a forward manner. That's called forward propagation. Inference GPUs can be a lot smaller, a lot lighter, a lot more power efficient typically. And you can even do this at the edge with smaller and smaller GPUs. So typically, these big training platforms take a huge amount of power and cooling, but the smaller inference and inference at the edge GPUs can take much less power, much less coolant. Some of these are designed to operate in fully remote environments. And the nice part is because you've trained it on a GPU, that model is going to be able to use the same architecture, and the code you wrote is going to be able to use that chip architecture in the same way. So if you kind of go down the GPU path, everything sort of just works. And compared to a lot of other types of hardware, they tend to be pretty ubiquitous. So that's kind of another nice part about why you'd use a GPU. Now, we're going to start going into slightly more interesting and exotic hardware. TPUs are a new development from Google. I think the first one came out in 2015 in an alpha state. And they've taken the concept the GPUs have taken to sort of another extreme. The whole GPU boom and its relation to AI, I think, was an accidental win for NVIDIA. I don't think that there was an intention or a thought that in 1996, when they were putting kind of their first GPU design together, it's going to end up transforming the AI community. But that was very much what Google had in mind. And so they've taken this von Neumann architecture and made it even more specific to doing matrix math. So where some of these other chips we looked at have an ALU, an algorithmic logic unit, the tensor cores here, they have much more specific logic units that just do scalar and vector math. And then they have this matrix multiplication unit that's processing these other units together against larger tensors, which is basically a multi-dimensional matrix. So a matrix that might have width and height and depth, and then you can keep adding sort of imaginary dimensions to it. So you can have a 100-dimensional matrix that you can't even visualize. Like there's no way to draw a picture of it, but within the math, it can exist. And these cores are designed to do just those functions really well. So they're basically useless for anything except for matrix math, but they do that job incredibly well. So they tend to be very, very performant. They tend to do deep learning training as well, if not in some cases better than GPUs. And they can do so typically at slightly lower cost and with lower power consumption. But again, they're a little bit less flexible and they can just do this one job really well. The same is true of AWS's take at these kind of specialized AI chips. Inferential chips are designed really specifically for inference, as you might be able to tell by the name. So these are similar to the TPU. They have a core that's designed to really focus on doing matrix math, and in particular, not even focusing on training. They're really focused on taking a model that's already been trained and then doing forward propagation through that model super, super fast. But they have maybe some of the best performance per dollar that you can find today. So a really great option if you're in AWS and your cost is a major concern. Moving on, there's another class of hardware that's getting more popular in the AI world, and those are FPGAs. That stands for a field programmable gate array. These can be super fast, or they can be super low power, and that's configurable by you, the AI developer. They're programmed by actually adjusting these interconnections programmatically. You basically program the hardware layout of the chip itself, which is kind of mind-bending. It's difficult to do. It has a pretty steep learning curve. Actually, I guess it would have a shallow learning curve because learning takes a long time. But they're incredibly flexible comparatively to designing a new chip yourself, because you can reuse this FPGA for another job. So the way that this would work essentially is that you would determine the function you're trying to accomplish. Maybe you want to build an FPGA that does a really certain tensor multiplication. There's like one certain kind of math that your model or your use case uses. You can basically reroute those interconnections so that your input and output blocks go to the specific logic blocks you want them to go to replicate some kind of matrix math. And then you can do that for both training or for inference. But if you decide it doesn't work or you made a mistake, you can go back and kind of programmatically change the function of this chip without again having to solder something new or build a new chip die. So it's a great combination of custom hardware but still being programmatic. One of the challenges with FPGAs is that they're just not as available. They're not built in as high a volume as CPUs or GPUs. The ones that are low cost and cheap tend to go out of stock really fast, leaving, there's this gulf in FPGAs where you can get them for $100 on a developer board, or they're like $5,000, and there's nothing in between. So they can be a little bit harder to get your hands on, which is one reason why a lot of folks don't lean towards using an FPGA unless they're doing some research and development. Lastly, that leaves us with custom ASICs. These are application-specific integrated circuits. And in fact, everything we talked about, TPUs and the Inferential chips before, those count as ASICs. Because what they've done is taken that von Neumann architecture and hacked it apart and kind of done their own thing with it. They still use a lot of the same concepts. They still use the concept of these kind of logic units and using caches and retrieving both instructions and data from memory. All of that's the same, but they've kind of reconfigured things to be focused on one job. This is the fastest possible hardware you can get. If you know exactly what you want your computer to do, if you want your computer to just take a picture of the sky and output the color that it sees, you will never get an algorithm to run faster than if you build a piece of silicone that does that one job incredibly well. So it can be lightning fast, insanely low power, but you have to custom design this whole thing yourself. And if you make a mistake, you need a brand new die. So you're now a hardware engineer as well as a machine learning engineer. So going down this path is like incredibly expensive, and that's why AWS, Google, they've created their own custom ASICs for this purpose. There aren't that many organizations or companies or people who have the time, the resources, the funding, and the patience to go down that path. So it's awesome. They can be incredibly powerful, but it's a huge risk and a huge investment to go this path. So they are much less commonly used in the machine learning space. So performance comparisons, right? We've talked about a bunch of different kinds of chips. Can we just get one chart to compare them all? The answer is no, not really. And the reason for that is that a lot of these hardware devices can be compared across a bunch of different metrics. So one metric is just plain speed of training a model or producing outputs. Another metric might be how much power it consumes. Another metric might be cost and speed per cost. And what you'll find is every vendor has a different chart that they'll show you that shows how their hardware is the best. So NVIDIA here has a great time to train for the combination of hardware providers that they've pulled from. These are from the same data set, by the way. So they pulled data from MLPerf, and now we see here that NVIDIA is the highest on NVIDIA's chart. Now, if we look at Google's chart, we see that the Google TPU v4 is better at the thing it's measuring. Now, it's measuring training time speed up, which is an increase in training time versus the time to train measurement. So it's like a slightly different measurement on slightly different networks. And then if we look at Xilinx's FPGA, you can see it's performing really well against another really specific subset of providers. So the answer is, it is darn near impossible, and I spent a lot of time trying to find a unified chart to put all this stuff in one spot. You really can't do it. So one of the important things to do is instead start thinking about the other factors that are important to you in your AI use case before you go and start trying to get into the nuts and bolts of specific performance, because a lot of these other factors, cost, where you're going to run it, what kind of software support you'd like to have, how expensive the hardware is, and how easy it is to find. A lot of these other factors end up being even more important than just the pure, speed performance. So I would say go down this path first. Try and get a sense of the kinds of non-performance related needs you have, and once you've got that figured out, then go back and find the combination of hardware that would meet those needs, and then you can do a more narrow performance assessment, and it becomes a little bit easier to get the data you need to do that comparison. So choosing the right hardware, how do you kind of like put all this stuff together? I'll share these slides so you can take a look at the details, but as far as machine learning is concerned, I think there's a few things that you can kind of take away from this. So for just general compute, just use a CPU. It is the best bang for the buck. Great for classical machine learning. Best software support in the world. You can use any programming language you want. Just there's hard to beat a CPU for a generic task. Now, if you're moving into deep neural networks, GPUs, TPUs, and inferential chips, I think they all play a great role. And the variance between those would depend on how ubiquitous you want the hardware to be, what cloud you're using, whether or not training or inference is more important, but they're all honestly great choices for deep neural networks. FPGAs, that really start to get into the realm of custom high-performance computing. If you have a use case that is so kind of bespoke and interesting and off the wall, maybe using really strange sensors that GPUs aren't working for you, an FPGA might be a good choice. And then for ASICs, you can do anything you want, but just recognize that the cost and the time is going to be astronomical. So it's not the first choice. It's probably the last choice you would pick. At least the last choice I would pick. So, hot take. This is my synopsis here, and I'm going to provide my Tiger King ratings. So CPUs get a Shiba Inu, GPUs get 1 Tiger, TPUs and the inferential chips get 2 Tigers of exoticism. FPGAs get 3 Tigers, and ASICs have 4 Tigers. They are by far the most exotic of the hardware you might run into while doing AI work. I'll share the recommended reading in our chat. So if you want to check out any of these materials, please do. This Elements of Computing Systems book, awesome reference to get a sense of how computers work and how all those bits and bytes interact together. So that's everything we had for you today. Thank you so much for the time. This was really fun. I hope you guys enjoyed it. And I'll be over on the general channel if anyone wants to talk further and dig into the weeds and or tell me what I got wrong. So looking forward to it. And thank you guys so much for coming.